Welcome to the final technical non-panel session to C++ and beyond, and we're going to talk about concurrency simply because anything else is too easy right after lunch. And in fact, I want to talk until, you'll notice today's schedule is shorter than the other days because we advertised that we would stop at 5 o'clock, and we actually went longer and actually planned to go longer because we came up with more material and just couldn't stop talking. It's a plague, I know, and when you're talking about C++, you don't want to stop. And so we went longer on the previous 2 days till 5:30, but because we told you all that we were ending at 5 o'clock today, we actually decided to keep to our word because you might have made plane reservations and so forth, so we're going to stop at 5. So this talk is going to end around 3:45, and then we'll have a break and our final panel as well. So for the next hour and a quarter or so, let's talk about C++ concurrency, in particular where we are today in the standard and what kinds of things are coming up next, both in the standard and in what we've learned, say, in the past year since we were here together at C&B before. For those of you who were here last year, here's an update as we look back as to how much has already changed and what we've learned in the meantime. As a motivating example, because I always like to start with a motivating example, let's say that you want to provide a log class. Notice the left and right-hand side are currently the same. We're going to fill in the implementations differently. But here's the goal. We want to let users take an object of this type and say, mylog.println, whatever the details are of what pretty printing we want to support, and have this code be correct without any external synchronization. They'd be internally synchronized, be thread safe, so they can just go call log print, log print, log print, log print, and we may interleave those messages, but each message will be atomic with respect to all others. So the order of the messages from different threads may interleave, but they're not going to interrupt each other, and they're not going to crash or cause undefined behavior because it's well synchronized. It's internally synchronized. So we could use mutexes, or we could use message queues. If we use, either way, we're going to wrap some sort of F stream, say, which is the standard file stream, and provide this println function. The question is, what goes in this white space so that we can actually have a thread-safe implementation? So here's a teaser. If we do it with a mutex, of course the thing you would do is to have a mutex inside the class, and then when you go to print the line, you'd go and acquire the mutex. In fact, it would be even better if you had a paren m paren in there somewhere so that the code would actually compile. First bug. So you get a lock on the mutex, do your thing, whatever the pretty printing is, and then release the lock. And so this will be correctly synchronized, right? If you were to do it using a message queue, then what you would have is a worker thread and some sort of queue to talk to it with. And in your println function, instead of taking a mutex lock, you would simply send a message, which is a functor, to the worker thread to be executed on the worker thread that does the work. And in this particular case, we'll go and notice we capture this. So the equals captures this. We capture the pointer to the F stream, so it's as if captured by reference. And then we send the message, and then on the worker thread, when it pumps and executes the message, then we'll do the work on the background thread. So we agree both of these are correctly synchronized. So tell me a little bit about the difference between the two. They both make this code work. They are both correctly synchronized, but they have different characteristics. Tell me about some of them, please. So you may not get a context switch. You get a nice, if you have a lockless queue, any internally synchronized queue on the right-hand side will do, yes. So by the way, the queue you're using has to be internally synchronized, just like the mutex is. It's a communication variable. Next to you. Your logging thread over here. Under this mode, the calling thread doesn't have to wait for the file I/O to complete. Very good. We have a cluster of hands here, yes, right behind you. So with the queue, we guarantee first in, first out semantics. depending on what the interleaving was of the threads as they arrived, whereas with the mutex, we don't. That may be true, although remember when we deal with concurrency, anytime you say ordering, there's always, keep in the back of your mind the escape hatch of, yes, that's one execution, but is it equivalent to a valid execution where they happen to arrive at the mutex in that order and just some threads ran faster or slower? So I have to think about it as to whether you actually have any different legal interleavings there, but that's quite possible. You certainly have a better chance because with the mutex, if everybody's piled up on the mutex, then whoever gets woken up, or if it's a thundering herd, whoever gets in first may not correspond to the order they actually arrived. Okay? Let's try this side of the room. I notice a lot of people talking about this side. Please.
Yes,
so in this case, the work of doing the formatting, as well as the I/O was mentioned, is done on the caller's thread, and we wait for it. Over here, all of the work, including the formatting stuff, is done on the worker thread, and we don't wait for any of it. So if you have objects which know how to stream themselves, then this could be more expensive. Well, that's true. I see, because you're saying if you take a copy of those objects, I'm eliding the details. I'm going to assume that if you're going to do this, that you'll capture them in an appropriate way, hopefully by reference if that's safe. If it's not, yes, you may have to take a copy. That's true. One more. Anybody else? Yeah, so the one on the left is synchronous, so you can talk about the lifetimes of things you pass in, right? Whereas this one isn't. It's asynchronous, which is why you have to worry about copies and such kind of thing. Which one would you prefer in your system? How many of you like the left-hand side better? Two lonely hands. And one, you can waffle on any question. That counts as a, nah, I'm not feeling strong enough to stand up for it. How many of you prefer the right-hand side better? Forest of hands. There's our thundering herd. The key difference between these two, the left-hand side is blocking, the right-hand side is non-blocking. So there's a few things going on here. If you do this, all the work is done on the caller's thread, like we said. You will block all callers. Callers will throttle each other. This can cost you scalability, but it doesn't involve any queuing overhead, so you don't get space overhead, but you get all these throttling problems, including even potentially anytime you block, you might, anytime you wait, you might deadlock, because that could be part of a blocking cycle if the work in here happens to somehow depend on the lock somebody else is holding in the wrong order and so forth. So even potential deadlock, if we want to be really telling scary campfire stories here, although you're unlikely to hit it, but it's possible. Over here, you're paying for a queue, but this is way more scalable. Nobody ever waits. Now, truth in advertising here, this actual work doesn't happen immediately. It waits and queues until somebody's ready to do it because it gets serialized. The caller, it never waits, is not blocked. And because of that, this is actually can participate in a nice wait-free algorithm, which is really cool, which is the gold standard for concurrency and what we should aim for. We'll come back to this. The talk in one slide is, as you can imagine from that intro, don't stop. We hate to block. I'm going to use the word block, wait. All of those are going to be synonymous, and we'll use them interchangeably. We don't want to go any of those places that are red lights. Now, what we have in the standard already is really good. We have a way to call functions synchronously. It's plain Jane code that we've been doing since the days of Ritchie. And you can conceptually think of this as blocking to call the function because it's executing on your thread and you wait for it to return before you continue. Well, now we have async, which lets you do that same function call, launch it asynchronously. Potentially, the default launch policy is here or somewhere else, and you get back a future, which means you could potentially do work concurrently with the execution of F until you need the actual result, and then you say result.get, and this might block. So you go from sort of reddish, always blocks, to yellowish, might block. If in the meantime the work is already complete, you can keep right on going. If not, at least you're that much closer to your answer. So we have a very nice tool for concurrent coding and talking about asynchronous values in C++11. We should use them. So when you need the value to do the next thing with it, you'll call future.get. When you just need the side effects to be complete, even if it's a future void, but you want to know the side effects are complete of whatever that task was, future wait is sufficient. And they both will block if the task isn't done yet, producing its value yet. This is great for usability because we can talk about future asynchronous values, but it is super essential for composability. It is urgently, vitally, desperately important that you be able to take library A and that launches some asynchronous work, and take library B that launches some other exotic asynchronous work that don't know about each other, and that they give you two things back that you can wait on together, that they traffic in the same types. Stood future is that lingua franca in C++ now of talking about asynchronous operations and handles to asynchronous operations or values. This is very important that you have this one very small but important common type that everybody can talk about. Unfortunately, that's a tale of the good. We'll get to the bad at the end. But in the meantime, let's talk about the missing. Because this is only half the story. What's in the standard now is exactly half the story of what we need. Fact of life. This is something we have just learned more and more, especially over the past 2 years, that blocking, waiting, ever is almost always harmful, even if it looks innocuous at first. So avoid blocking like the plague or whatever else you would like to malign in there that you think is the most horrible thing on earth you want to run away from. Blocking is worse than that. As data points, if you look at the most current and cool and responsive applications, iOS, Windows 8 applications, one of the key reasons they are so responsive is not just because if they're written in efficient languages, they can run faster on lower power processors. That's nice too. But by far the biggest reason, much more important than that even, believe it or not, is they don't wait. They're designed not to wait to stay responsive. They don't do work on the GUI thread so that it doesn't take input while it's doing some other work that could have been done asynchronously. For example, in Windows 8's newest APIs, if you look at the WinRT APIs designed for the new tablet-style apps, those APIs are 15% of them are asynchronous. Furthermore, asynchronous only. You can't call them synchronously unless you tack on .wait at the end explicitly and say, no, I really want to be stupid. And if you think about what that means, 15%, that's a huge number. It's like 1/6 almost. There's a huge number of those APIs. So what was the criteria that led to that 15%? Well, the Windows 8 designers, the WinRT designers decided that any API call that could possibly take longer than 50 milliseconds, 50 milliseconds, had to be asynchronous. And in fact, actively prevented you from easily calling it in a synchronous way, so as to not shoot yourself in the foot, so that your applications would stay responsive and fluid, which is quite draconian, but nobody's complaining when they're scrolling through and things stick to the finger and everything's gorgeous. So this is more and more where life is going. Even in Windows 7, a huge number of Win32 older APIs were made asynchronous because, for instance, the Office team required that create file be made asynchronous so that they could be less blocking. So the world is only moving more in this direction, and we should avoid blocking like the plague. So what is missing is we have these blocking functions to wait for a future. We can get to wait for a future. We can wait to wait for a future. But we just said avoid waiting like the plague. We don't actually want to use these if we can at all help it. This is news that we're all learning. So what do? What we want to have is the other half of futures, which is a way to not block on them. And so the styles that are being proposed now for standardization, and the committee is actively looking at, and Microsoft has some libraries here that we've worked on and are contributing to the committee, and everybody's giving their feedback and bringing it forward, is to add a .then and as a complement to .get, and a when any and when all, which correspond to .wait. So instead of wait and then do something when side effects are complete, it says, well, whenever that's done, here's something more to execute. You give it something that's executable, like a functor, like a lambda. .then, instead of saying .get and do something with that value, you say .then, so whenever this value appears, do this with it, and just immediately continue so the caller is never blocked. Let me illustrate. So here are the two versions that we already saw. We have synchronous calls, plain old function call, And we have now the asynchronous call where we call something like async, it returns a future, and then we can do other stuff and then call .get when we need the future. And that may block. But at least we're that much closer to our answer. Here's what .then would look like. We still launch the same way because the launching is already asynchronous. So async is great for our purposes, or whatever future thread pools or launchers may come into the standard. That's independent of this because we launch the work asynchronously, and that's great. Then the code in here runs concurrently with this function, as before. That's still great. But then finally, when we want to use that int, what do? Instead of calling .get and saying, now I, the caller, am going to wait for it, there it is, and then do something with it. We say, no, I know what to do with it. I'm going to say .then, let me get it back, .then, when it's available, take that integer and then do this with it. But what I do as the caller is I say, here's what to do. I stick it in the future and run away and keep doing what I'm doing. I don't wait. I say, do this whenever it's ready, and off I go. Because I know what needs to be done, and that can be done whenever the future is ready. Questions? So why couldn't, just like you say, the question is, just like you say auto result equals async this, why couldn't you here just say auto result 2 equals async, do something with f.get, right? Yes. With result.get, rather, yes. Wait for it. We'll come to that. If you do it that way, that will work fine, and that's going to be one of the workarounds. But you will have you will most likely have an extra context switch and wake up, and you'll occupy a thread in the meantime. So it's going to cost you occupying a thread and a wake up. Ain't free. There was a hand over here. Was that answered? And you could, in this case, if you already know what needs doing at the time that, like say, if this code is all in the same scope, yeah, just stick go and use f.xyz all in the first lambda. But very often this code will be distant, and this will be written by one person in one module. You'll pass it back somewhere else, and then you'll have this in some other module. So it's nice to have them decoupled. Besides, you may want to do this several times. Do this, then do this with the result of that, then do this with the result of that, and you're building yourself a chain of things where nobody ever waits. And now I want to be clear about one thing. I'll take your hand in a second. Clear about one thing. We call this a non-blocking mode. We do not block, we don't wait, we have little dances, and it's great, it's a party. There will be people who will technically point out that's not completely true, and they're right, but what they're going to say is there is task waiting and there's continuation waiting. So your task, your caller, is not going to wait. Because you just say, here, do this, and run away, and we're going to keep doing our thing, knowing it'll get done whenever that thing is available. Of course, that work itself is going to wait. That work itself is not going to get executed until the value is available. But that can't be helped. So we call this, even though this part does block, we call this a non-blocking style because it does not block the caller. What if the result variable passed out of the scope? For example, what if you returned it to somebody? That's fine. It's a future. It can travel around. You can store it in a global variable, store it on the heap somewhere, come back to it an hour later on a different thread, and say .get or .then. You're allowed to do that. So the question is, and you're thinking of what Scott said on day one, and I'm going to get back to later at the very end of the talk, so hold the thought. The short answer right now is, you're saying, what if this is all in one function scope, say? I do this, and then I return. Don't we wait for, doesn't this future, this wait automatically? Well, I'll come back to that at the end, but you don't have to do that. You can return it. You can convert it to a shared future and put it on the heap somewhere. So that's one possible thing that could happen, but it's not the only thing. You could store the future somewhere else. You could return it to the caller. Futures are movable, and there's also shared future if you want to take multiple copies, as many as you like, and scatter them all over the place. And then this will outlive the function scope. But I will come back to that at the end. One more and we'll continue. So the question is, when I said, and we'll come back to the workaround, that if you just repeated the async here, instead of saying result.then, you said auto result 2 equals async, blah, 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 go and use r.get, say. And I claimed that would cost you a thread. And I should say probably, because the default launch policy and so forth. But why does .then not cost you a thread? Well, the answers are that you can have many options for scheduling, but an obvious and easy one is whatever thread finished that task, as soon as it makes the value, immediately without any context switch or blocking, goes and immediately runs the continuation. So that way, there's a thread that was running anyway, and there's no context switch, there's no waiting, and no wake up. So you can make this more efficient by having expressed it this way. With that in mind, we love this because this never blocks. And again, when we say never blocks, obviously this work is going to wait until the value is ready, but we never block the caller. Just like async on the function launch doesn't block the caller, now we're solving the problem that we're making the function result taking asynchronous so as not to block the caller. So now the question that you've already started asking is, well, hopefully the standard I've promised will consider including this. What can we do until .then? Pardon. I'm sorry, but not very much. Option 1 is use a library that has it. I happen to know one. And if you use Visual C++, for example, 2012, and use PPL task, task of T is very much like future of T. We deliberately named it something different than stood future because we didn't want to get in the way of standardization, but think of it as future of T. It happens to have a .then, as well as the when any, when all helpers. So that's one thing that you can do. And especially if you use auto, then you may well be insulated to the type changing later when you get a standard conforming implementation, should this become standardized, and the type change from task to future. So that's a nice path forward. The other way, which we've already discussed and has already been suggested, is, well, couldn't you just turn blocking into non-blocking by more async? After all, some is good. Right, so use async again. Now, it's at the cost of occupying a thread. And we could either call async, or you know what, if we're so happy about this and we do it all the time, why not write a templated function with 2 template parameters, Andre? Because if one is good, more is better. And have a trailing return type and use decal type and in 3 lines, it's wonderful. Now I can write, instead of f.then, I've got so close I can write then comma, then f comma. There's a win. At the cost of occupying a thread. This is a workaround. It's not as efficient as if .then were supported directly by future. But it works. It works. It also compiles. I tried it. So here's a useful fact. You can always turn blocking into non-blocking by waiting, and that costs you nothing. So that if you get, non-blocking into blocking. So if you have a future, if you have to do an async call, and you just need the result right away, it's an asynchronous call, but you just need the result right away, there's nothing else you can do, and you want to wait for it, easy, just tack on .wait. Go f my function, parameter, paren .wait, paren semicolon, and you just made it synchronous with no overhead. You just spawned it, no overhead beyond what was already going to be happening to spawn the asynchronous task, because you wait right away. If you want to go the other way, you can always turn blocking into non-blocking, the good thing. You can turn the bad thing into the good thing by applying async or the equivalent, some other way of launching async work. That's a standard way that's very good. And at the cost of occupying a thread, and you're borrowing a thread that you're going to be sitting on. It's going to be quiet, it's going to be quiescent, but you're going to be borrowing it, and then after sitting on it a while, you're going to get a wake up. So there'll be that overhead. There was a question near the back. No? This side. So if you call .get, you know it's going to run on your thread, you have control. Your question is there going to be some way of saying a scheduling policy so that there'll be some default, which is nice, presumably continue running this on whatever thread produced the result, if that's possible, or having a schedule and execution policy? Yes, and in fact, both Microsoft and Google have proposals about that, and we're working together on this proposal. So Jeff Yaskin and Chandler Caruth at Google, and our folks, Nicholas Gustafsson, and Artur at Microsoft are working together on this proposal to see what the best way is, and we're getting feedback. So we got some feedback on this in May at the concurrency subgroup meeting, and we're going to get some more, no doubt, 2 months from now. But lots of people are working on this to make sure you have the right kind of policy. And in fact, that scheduler that execution context, which I think is one of the proposed names for it, might even be something separable you can use in other places too. So I'll leave the details alone because they're still in flight, but yes, you will be able to have some control. If we do this, never assume anything, but we hope to do this, something like it, then you would also get some control. Yes, so the question is, it could be that since you have this idea of dot then, you might want an async with a chain where you say, get the result, do this with it, and then get the result of that and do this with it. And it's what you already saw. With dot then, it turns out that most of the use cases that we've been discovering, at least in the last year or so, by the way, this is available for all that asynchronous Windows 8 programming with PPL. That's one of the reasons why we had to do it, was to make sure it was as future-like as possible, but worked really well with all the Windows 8 asynchronous stuff, so it works nicely in C++ as well, at least in this compiler with that non-standard extension, yet non-standard. One thing we found in practice is the average number of dot thens you write is 1. Because you typically launch something, and you know what you want to do with it at the end, either at the launch site, in which case you put it right in the original async, or you get the thing back and you know then or pretty soon what you want to do with it, or you pass it back to one guy who knows what to do with it, and you typically call dot then once. However, sometimes another pattern, which is not the most common case, but it also happens, is you see dot then, dot then, dot then, as not in the same scope, but as each, say, caller, as you go back out through a call tree, or you pass it along for different stages of processing, tacks more things on. And you've expressed your program as a nicely beautiful set of small work items that can run asynchronously, and yet be deterministic, and you can reason about your code just reading it, and that's a very powerful thing. So having said that, there's a useful fact. However, this brings us to the second part of our two major parts. I wrote an article called "Sharing is the Root of All Contention." That was the name of the article. It is very true. If you haven't read it lately, please read it. Read it on your way home, read it at home, read it to your children if they can't sleep at night. I assure you it will solve that problem. Works great on wives too. It puts everyone to sleep. But the point is, as long as anything is shared, you immediately, without even thinking about how is the sharing managed, is it multi-threaded, are you using mutexes, the threads, are you using queues, you know you're going to have contention. If you see two kids fighting over the blue crayon, right, it starts in kindergarten, and it only gets worse from there. So if you have, for instance, just as an aside, just to show that just anything shared is just evil and causes contention, and so we try to avoid it. How many of you enjoy reader-writer locks? I talked with some of you about this yesterday. How many of you enjoy reader-writer locks because they scale? I have bad news for those of you who put up your hands. They scale better than non-reader-writer locks because you can have multiple concurrent readers. As soon as you get over the euphoria of that, and you have multiple readers in flight at the same time, and you start scaling beyond one at a time, and you think everything's great, and you're about to turn your back and go home for the weekend, you hit the next barrier as things slow down, and you have your next scalability barrier. And why do reader-writer locks not scale very much? Counting the readers, who said that? Counting the readers, which means you have a reference count or a reader count. That is a very popular hot little cache line. Everybody wants a piece of that. And a cache line that people are trying to mutate, even if only one person is mutating it in a loop, is going to throttle all processors who are trying to use it, because only one in hardware, it's like a hardware lock, can use it at a time. And it's because of that count. Even that little bit of sharing, that little bitty count that couldn't have hurt anybody, will become your next bottleneck. So sharing of any kind is the root of all contention. We would like to avoid it. Now, let's talk about when we do have to have shared objects and resources. We would like to avoid these where possible, so that's my preface. However, sometimes you are going to have them. When you do have a shared mutable object in memory, you're going to have a data race unless you synchronize access to it. And so the usual way we do that is using a mutex, right? Just like we had in the left-hand slide of the first slide. Use a mutex, you grab the mutex, waiting if necessary, you enter your critical section, do your stuff, and unlock so the next person can get in, right? It's synchronous, it's blocking, but it's correct. That's the basic tool. A very common pattern, which is often abused in an anti-pattern, but sometimes is correct and useful, is to have an internally synchronized object for historical reasons from back in the day, because this was invented at the very dawn of computing, like most useful things. It's called a monitor. Java people will recognize it as a synchronized object. And again, that's often an anti-pattern. It gets abused when it shouldn't be, but sometimes it's the correct thing, where you take a lock per method call, for example. Every member function you call takes a lock, does its stuff, and gets out, so that you can use this object without any external synchronization and just call member functions on it, and it internally synchronizes them and runs one at a time. This is the tool. This is the pattern that or one of the patterns we may build on the tool. What we're missing is this bit. What do we do? What tool do we use for non-blocking, and what kind of pattern can we wrap around that is the non-blocking version of this? So to see that, let's now just push that on the stack for a second, and let's go solve a general C++ problem. Two of them, in fact. We'll come right back to that question. But first we want to solve a general C++ problem. Let's say you want to write a wrapper, like call it wrap of T or monitor of T, which presents the same interface as T. So if T has a .append member function, because maybe T is a vector, you want monitor of T to have a .append member function. How do you do that? So here's the first problem of the two problems, generalized wrapping. Let's say you have a widget W, because widgets, unlike gadgets and thingies, are the correct true example type. And after, Scott, it just blows me away that after 20 years of widgets with occasional gadgets when you needed a second type, I finally caved 2 years ago and began writing widget, all lowercase, to be more standards conformant, but we won't talk about that. And then you start switching to thingy today. What's up with that? So we're going to have to talk about that. You've grown. Don't you know you're setting an example for others? You should have grown 20 years ago. So we have widgets in Scott Meyer's honor. Widget W, if we can say widget.append, w.append hello, if that's possible, we would like to have a wrap of widget, also allow wrapper widget.append hello. My question is, how can you build such a generic wrapper in C++? That duplicates the interface of the wrapped type. Hey, it's a powerful language. You can do anything, right? Like a smart pointer. I don't recall that you could do that, except that a smart pointer doesn't give you access, doesn't duplicate the interface. So yes, because what you can do is a smart pointer lets you dereference, so it gives you access to the object, and that's one valid way of doing it. The one thing it doesn't do is it's not going to solve our second problem, because once you do that, you relinquish control over what happens to the object. You can't get in the way anymore and do any processing you want to do. For example, if you do that, it's not clear to me how you can call how you can make a monitor of T which puts a lock, mutex lock acquire release around every function call. You may be able to do it, but there are some edge cases that would concern me. And it's not going to solve the second problem, which we'll get to on the next slide. So that's one potential approach. Anyone else? Derive, like every good object-oriented programmer would do. What if we look at this hint? Consider that widget is a type def for stood string. Does inheritance work? Not super well. So that's not to mock it at all, because that is a perfectly valid answer, and that is the way this would be done in a pure, more, quote, pure, unquote, object-oriented style. And you could get away with that in a language where basically everything that you ever see is a virtual function. Although even then, how do you know which ones to enumerate? The next thing you want, if you do that, is you really want reflection. So you want everything to be virtual, and you want reflection so you can know, or even without virtual, if you had reflection, maybe you could sort of make up the interface line by line as you go. If you're using D, you'd probably create strings containing more code and then compile them in line, just because you can. But even then, some things are hard to wrap. Like, for instance, if you have constructors. Constructors are notoriously difficult to wrap. And operators. Non-virtual functions, there's a key one. Templates, including templates that might be specialized. You can't partially specialize function templates, but you can specialize them. And all of these things are a very rich algebra of things you can do in C++, an algebra of a type you can express. But it's hard to wrap them all. So what are some solutions? Well, we talked about make everything virtual. Well, not every virtual method can be virtual, nor can it be. Constructors, for example, are not virtual and, in fact, don't behave virtually in C++. You need an init function or something like that. Now, we have inheriting constructors, but it's not quite the right tool. We still can't reflect, and so we can't make up all the functions as we go. So maybe we can step back and maybe go back to the smart pointer approach, but with a variant. But first, let's look at the second problem, because we want to solve two problems at the same time. Here's the second problem, which is sort of independent of the first. Let's say I have more than one function call that needs to happen atomically in some way together as a transaction that takes the system from one valid state to another. So credit Bob with $100, debit Mary with $100. You want to somehow synchronize that so nobody else gets to see the system in a state with $100 too many in the system. Otherwise, your ledger doesn't balance. Or let's say you say log.print hello, salutation, first, last, today's weather is getweather.com location. But these are two function calls. Maybe you want that to be a single log message, not interleaved, where you get the hello, Mr. Herb, and then some other stuff, and then Sutter, today's weather is dry, which means I wouldn't be in Seattle, but let's assume. So how do we make these things, these multiple calls, which could be arbitrary size, because that last one could be 3 or 4 function calls if I just wrote more semicolons. So what are the problems? Well, we learned some things with Java synchronized objects. We learned some things with C++ copy on write strings, which are now banned in the standard. Implementations that have them are not conforming, but we're still migrating away from that. But we've learned our lessons. The first thing we learned is that locking per method call is the wrong granularity, because it locks not enough, because there's no lock around, say, both of the account credit and the account debit. It's lock, credit, unlock. Lock, debit, unlock. It's missing a lock. It's not enough locking because it doesn't cover the whole transaction. And to add insult to injury, it's too much locking because it's locking every single function whether it's needed or not. So this is one of the classic problems with the monitor pattern and with copy on write strings and such kinds of things. Java synchronized objects when not used appropriately. So per method call is not always the right granularity. Then the second thing, which some of you noticed on the very first motivating slide, is where does the actual work get done? Because if I just do, if I lock, then I'm doing this work on the caller thread, but also under the lock, which means I'm holding the lock longer. And in this case, notice that last piece of code. I've got a web service query. Who knows how long that's going to take if I'm on a slow Wi-Fi connection. So I'd like to avoid doing work also as a secondary separate point on the caller if I can help it, and certainly under a lock if I can help it. So now let's solve these two problems in C++11. And the syntax is not exactly having a wrap of T have the same interface of T, but it is oh so close, and it does overload an operator, although it could be a function call. Here is the complete solution, which is generic. You have a wrap of T, so it's parameterized on a type T. It will store a T object internally, of course. You know it's going to have that, and whatever that other state is that the wrapper adds. You provide a constructor with the nice brace initialization, and all sorts of good C++11 stuff. And then your payoff is you have one more function, which I just happen to choose to call the function call operator, but you can give it a named function if you want. It takes anything invocable with a T, returns you the type of invoking it with a T, and invokes it with a T under whatever the wrapper work is that you want to do, which can be before, during, or after all of this work, and then returns you the result. if you use this pattern, the calling code looks something like this. So instead of an x, where I say x.accounts, and x.balance, I can say wrap of xw, and I call w with a lambda, w open paren lambda, that takes the x. You hand the x to whatever work the caller gave you, and he can do whatever he wants with the x directly using natural code, as much as he wants, as a single transaction, indivisible, and we can do whatever wrapper work we want around that and then return the result. So the transactions are natural. The caller writes normal code. This is a nice thing. So when you think of this pattern, here's how you apply it to class monitor. So Java synchronized objects, this is the same idea. Here's how you would do it in C++11, a very nice, convenient way. You have a T that you hold, you have a mutex that you hold, and in your function call operator, you take, the caller can give you anything. Lambdas are fun, but it's not only lambdas. Anything, any function pointer will do, any functor type will do. And this is const because we're not modifying the state of the wrapper logically. But what we're going to do is take a lock and then under the lock perform f of t, return that value, and unlock. And now there, in a few lines of code, we've written a complete monitor where I can call that with arbitrary code and it will be synchronized. Now, by the way, you'll notice that the word mutable has come up a couple of times. It just happens naturally. Why? Because this is logically a const function. I'm not changing the wrapper state logically from a thread safety point of view. This is internally synchronized because I'm taking a lock guard. Now, certainly the mutex, I'm not really logically doing anything with it. I'm just locking the mutex, but I know that's safe because it's already synchronized. So for the reasons we talked about on day one, the mutex is mutable. But what about t? If t wasn't mutable, I couldn't call this here because what if f took a non-const tref? I wouldn't be able to call that here. So we might say, well, isn't it kind of an abuse to make the t mutable as well? No, because mutable means thread safe. And thread safe means either one of two things, bitwise const or already synchronized. It's synchronized. Therefore, it's perfectly appropriate to make that mutable because it does not, it's internally synchronized. In fact, that's the whole point of the pattern. That's why the data members are both mutable. Key thing, if you see a data type with all the members mutable, you know it's an internally synchronized type. Because that's what its whole purpose is, and to protect the shared state this way. So there's monitor of t. Here's how we might use it. Let's say we have a monitor of string. We'd probably have some more interesting type, but strings are fun, so let's just do it with a string. Besides, string has, last time I counted, 113 member functions, constructors, templates. And so, you know, what's a few? It shows we can wrap all that in just a few lines. And here's what you can do. I have monitor of string, and I initialize it with some value. Notice I can construct it just like a string because it's got that constructor that constructs from a string. Then I'm going to, in a loop, just start launching some async work. You'll notice the async work going on here. So I'm going to launch a bunch of async work. I'm going to start a first transaction. In that transaction, I want to say, OK, I want to use the string. So I just write this little incantation that returns me the internal string, and I can do whatever I want with it. This is guaranteed to run under the lock. So I can append to it. I can append a space. I can append toString of I, which is standard now, by the way, in case you didn't know. ToString, we now have in the standard. I know, it's such a long time. And then even on another line, do another function call. So there's multiple function calls going on here, but it's OK. It's all a transaction. It just naturally works correctly. There's going to be no interleaving in the middle of this. And then I finish the transaction down here. Then I start transaction number 2 to output it. And again, that's going to not interleave with any other work. And remember, I'm doing all this in a series of async calls that I'm spinning up. So there could be a bunch of these transactions happening at the same time. Good thing it's synchronized. And then at the very end, I'm going to go through and wait for everything. So what does this actually look like? Well, note again, here I've got one transaction. Here I've got another transaction. Here are actually 2 possible executions in different colors that I got on my actual machine. And you could have lots of more interesting executions. But the key thing I want to point out is that this first transaction, we can clearly see, was never interrupted. So that worked correctly because toString of I pick a space, toString of I, and append a new line. And obviously, I'm not getting any torn lines there, so that worked correctly indivisibly. Also, my writes to cout happened indivisibly. Hooray. Now, the order in which these transactions interleaved was different, but that's what I knew I was getting. I'm saying here are the transactions of each thread, so of each async call happened in order, but of multiple threads could be interleaved, but they were correctly synchronized, so they would go one after the other in some legitimate order. Now, if you look at these executions, if you get down to these first bars, what's interesting, what can you say has happened when we get to that bar? How much of the workload have we executed? So we've got every thread is doing one transaction, or two transactions, it's doing one transaction to cobble together a string, and then a separate transaction to output it. So if we get to those yellow bars in each execution, we know we've done at least what? Yeah, we know we've launched all of the asyncs, and we've executed at least as much as what of each async? The first transaction of each async, right? Because somebody eventually did a cout of the whole string, and of the string, and we see that all of them have been created. So we've written all of the 0, 1, 3, 4, 2. It happened to be in that order that the asyncs created them. But we know all of them have done at least this much. And then we go and we drain the queue of printing out the other, running the other transactions, and they go and print out the rest of the string as we keep adding and adding to this string. But it's all nicely synchronized. Any questions about that? I know Scott has a question about that. It's a very, very good question. What's your question, Scott? He has no idea I'm going to do this. Your question is about this. What's your question? Why is it not a polymorphic lambda? I know. Why don't we have polymorphic lambdas? We should have polymorphic lambdas. You're right. Post C++11, Scott mentions this every time I talk about lambdas, so I knew the question was coming. And he's completely correct. We should have them, because once you have them, then this pattern gets really slick with very little syntactic overhead. Because basically, this would be one of the potential syntactic shorthands for the parameter being autoref, the type being autoref. We don't have that yet, but we can still do this, which ain't half bad. Now, we don't have to limit ourselves to a string. Did you ever want to synchronize cout? We just wrote it. The monitor of T already does that. We just have a monitor of ostream reference, because remember, we can't copy, and we don't want to copy that cout. We want to use the cout that's already there. I'll just wrap it. Now I have a monitor, notice I'm saying of ostream reference. Now I have a synchronous cout. I initialize it with cout. And this is exactly, I think this is exactly the same code, roughly, I had before. Here, I'm just doing something different in the actual print part of it. And as I go through, here's one potential execution. And you can see how this is all very nicely ordered. We don't get messages interrupted. The messages as a whole interleave one after the other correctly, but they don't interrupt each other. They don't conflict. They play nice. Nicely synchronized. And I could even print done after I join. And I remember to use sync cout here, not cout, because then that way everything's synchronized. Pretty neat. So I can wrap anything now that I want to. And in post C++11, this gets even nicer with polymorphic lambdas. You can't do this today, but you can do this today. This soon, hopefully. Now, but wait, recall, I've been spending all this time, you've been letting me get away with all this time talking about monitors and mutexes and waiting and synchronizing, and you've let me off the hook because I just preached about a half an hour ago saying, blocking is evil, we never want to block, and blocking just ruins everybody's day, right? And yet here I've been talking about doing all this blocking. Well, that's to illustrate what you can do today with the standard mutex and a monitor pattern and how to make this nice wrapper of T. By the way, that whole wrap of T idiom, I've never seen before. I'm sure somebody else has invented it first, but I've asked a few people like Stefan, and nobody else has seen it, so maybe it was first invented. I'm sure somebody else did it too. But the idea of holding a t and then overloading the function call operator or some other named function to take any function, any callable functor, and then just under the wrap, give it t to do whatever it wants to with it. This solves the generalized wrapping problem because you can have access to the full unfettered interface of the t, and it solves the transaction problem because you naturally express what your transactions are, which could be a single method call or could be as complex as you like, including side effects and I/O. Cool little pattern for under 10 lines of code in C++ 11. And of course, you call it with lambdas, and then it's just bliss. But wait, blocking is harmful, and I've been showing you how elegantly to write blocking code. This is not a net good for the universe. Remember, we said avoid blocking like anything you hate. Hate it more. So what are we missing? Well, we have a mutex in the standard. We have several of them. What we are missing is a message queue. This is a fundamental primitive for non-blocking. Remember we said you can always turn blocking into non-blocking by changing a mutex to a message queue. Most people don't think of a message queue as a synchronization tool, but it is. It's the exact analog of a mutex. It's just the non-blocking version of a mutex. It's the basic tool you use, and then of course you use it in conjunction with a worker thread. So you can do a mutex and do all the work implicitly on the caller's thread, or you can use a message queue and arrange for there to be a thread that services it, or more. This is your primary tool. We don't have this in the standard yet, but we're now working on proposals to get one. Yay us, to quote Scott. You can see what an influence he has been on all our lives. And what we really want is not a monitor of T, although we've been wasting our time talking about that just because we can. We want a concurrent T that we can just fire things at, and they will just run asynchronously, and we never wait for them. How hard could it be? Remember, you can turn blocking into non-blocking by replacing a mutex with a message queue. This is a very useful fact, especially because we hate blocking and we love non-blocking. So we want to know the right incantation to get from bad to good. So remember, this is what we wrote as our monitor of T. I added some more space because now we're going to write concurrent of T. It's going to fit on one slide, but it's going to take a couple more member variables, and otherwise it's going to look just like this pattern. Remember, monitor, we just took a T and a mutex that protected it, and then in our function call operator, we take anything you want to do to a T, we take a lock, and let you do it to the T. Arbitrary code, we don't need to know what the interface of T is. This is wonderful, nice separation of concerns. Then we release the lock, and off we go. But this blocks. To turn it into non-blocking, we replace the mutex with a message queue. Right, we've all been awake. So we change it to, say, a concurrent queue, and I'm italicizing that because it doesn't exist yet in the standard, but some internally synchronized, probably lock-free concurrent queue, a message queue, of stood function. And what you do, and a stood function of void paren paren, takes void, returns void. What possible use could that be? We'll see. So notice I also added a stood thread, because I need a worker thread. So each one of these concurrent of T's is going to have its own worker thread. In the constructor of the concurrent object, obviously I have to initialize the thread somehow, so I do. I initialize the T as usual. Yeah, the order is important here. Initialize the T. Notice the thread comes last. This is important because it's going to start running asynchronously and start using this stuff. So make sure that you initialize the thread last. Of course, you need to give the thread a function to call. Well, I know how to write a lambda as well as anybody, so there is the entire thread mainline, which is kind of neat. As I mentioned, we love lambdas. So the thread just says, while not done, where done is this flag, pop the next thing off the queue, and I'm just going to assume pop is a blocking pop, which if there's nothing there, waits until something is there, and then wakes up and pops the next element off the queue, and executes it. Notice the extra set of parens. So it just sits there, wait, take the next item, execute it, take the next item, execute it, take the next item, execute it. Who sets done? The destructor of concurrent, when you're done using this, so you've constructed you've created the concurrent object, you've done things with it, and now you want to destroy it. You don't need it anymore. But it's got a thread. It may still have things that it hasn't executed yet that you gave it. So what we do is we push a little lambda that sets done to true. And then we wait for the thread to join. What this will do is the thread may have already some work queued up. We'll simply, after all that, enqueue one more little work item, which as the thread goes through and executes each work item, it'll finally pick up ours, execute it, which happens to set done to true. Go back to the loop, check not done. Oh, look, it's no longer true, and drop out. Which is nice. It has no idea that the last work item it executed just told it to stop, but that's an easy and convenient way to do it. Finally, here's the major function. Here's the one that gets the limelight that we've been waiting for. It's exactly the same pretty much as before. It takes any type that I can pass a t to, and it simply, instead of taking a lock and then executing f of t and unlock, it says push a lambda, which when executed will run f of t. Where is this lambda going to run? In between these braces sometime on the worker thread. So what I've done is I've now created an object which spins up a thread on construction, and it owns this t, whatever I give it. It lets me pass any work I want to do to that t, executes it one after the other asynchronously. That's all queued up, so callers never block, never wait. This is a non-blocking call for the caller. And gets nice orderly shutdown because at the end, and if you've seen my effective concurrency course in the active object pattern, this will look familiar. It's a similar idiom. We simply enqueue a message to say we're done, to make sure we drain the queue properly. This is the only method call on concurrent that may block, because we do orderly shutdown. We wait for the queue to drain, all the work to be done, and then we just destroy everything and go home. Now, there's one thing missing. First of all, before I ask for one thing missing, any questions about how this operates? So what's the one thing? Oh, Scott, please. The question is, why doesn't done need to be atomic? That's an excellent question. And the reason is because it's only ever read or written on the worker thread. So the thread mainline reads done, and the only one who ever sets done is a message. But that's a very important question. It is very subtle, but very important. Notice in this pattern, we do nothing on the caller's thread. Absolutely nothing on the caller's thread except q.push and construct a lambda. And then we run away and do whatever else we're going to do. By the way, this is cool because it means that whatever work the caller gives us, with the monitor of t, it was done on the caller's thread, and then to add insult to injury under the lock. Here, all the work is handed off to the background thread. We don't even do any of the work on the caller's thread. We simply construct a little lambda, we push it into a queue and run away and do the next piece of work that the caller has, that the caller never, ever blocks, never waits. This can be used in a wait-free algorithm, which, like I said, is a very high bar. Question? Yes, this assumes that the pop function, if something is already in the queue, it will return immediately without blocking and execute it and keep going. But if nothing is in the queue, it will block and then wake up. So this worker thread may block while there's no work to be done. Why consume the thread? But the caller won't block. And again, in full fairness, this continuation, it's still the continuation style, the piece of work you give it, will also block. It's the caller who won't block, and therefore we call this a non-blocking. It's a wait-free algorithm for the caller. Obviously, the work is synchronized, but it's synchronized somewhere else where we don't have to worry ourselves about it and we can keep going. Now, let me ask what's missing from this version. So if there's information being shared between threads, including, say, this worker thread, concurrent of whatever, and something else, you still need to do synchronization. That's true. But what don't we have here that we had with monitor of t? This is deficient in one important way. Return value. Why? You don't like void? What should it be? Well, we'll come to that. We should have a better return value. I will solve this problem later in about 3 slides. In the meantime, let me show you how this works. You see this code? I hope it's familiar, because this is exactly the same code we wrote before, except at the top, instead of saying monitor of string, it says concurrent string. It gives you exactly the same interface. The code, the calling code, is exactly the same. The big bonus about this calling code is this calling code never blocks, except in this example, we wait at the end. But none of these calls ever block. We just go zipping and express the work and keep right on going. And now, notice that when you look at the output, you can see that in this particular case, because everything's so concurrent, I happen not to be able to easily get a run where the first transaction had all ended without the second transaction almost all ending too. So we have different orderings, and they're nicely non-interleaved, but notice that we have got the two with some interleaved execution of the work, but we never break up the work. It's indivisible. Each one is a nice transaction that is run on some other thread. In fact, do you notice that we write done to see out? When is it written? So you can see how asynchronous it is. Now, there was a question at the back. Hand went away. Question here. Oh, and lest I forget, sorry, for Scott, yes, we ought to be able to do this with a polymorphic lambda, but this works today. This will work tomorrow. Isn't it so cool? Your question. So pop blocks if there's nothing in the queue. So we try to avoid spinning here. And the idea is you would want to use a concurrent queue that has the equivalent of this operation. And so it might, the spelling may be different on a particular queue object or class you have. But the idea is you have a pop which waits if there's nothing, blocks, lightweight, and then is woken up when somebody pushes something into the queue, and then wakes up, gets it, and then we execute it in a loop. Of course, if there's something there, we can keep right on going. So here, notice that we launch all this work. This is a very good question, because you think, wait a minute. In fact, I was just looking at this myself and thinking, did I run different code than I compiled here? Because I was tried very hard to compile exactly the code I ran. But I think that you put your finger on it. I launch all the work. I wait for these threads which were launching the work. Then I write done. Here, and by the way, with done, I happen to get lucky that it didn't interleave with something, because of course I'm doing that thread unsafely. But for a demonstration program, yeah. The key thing here is, so that done, the done here I can explain. The done up there means I finished launching all the work, I printed done, but the other objects, but then after this in the main line, as soon as I get to the next close brace, the end of scope of concurrent string, what do? I destroy the string, the concurrent strings. I NQ, or to the one concurrent string, there's only one. I NQ, done is true, and block and wait for it, so it's still orderly shutdown. I'm not having something extend beyond the end of main. And I wait for them to drain their queue. That's why some of their work could happen after this, because this has launched the work. And in fact, that done up there is a poster child for how asynchronous this is, that I've not blocked the caller. I can prove it. There is an execution, and you can try this at home. One more question. Let me try to pick a new hand, and then we'll continue. Yes, I think you're new. So the question is, can this be abused? Absolutely. And in particular, one of the concerns people have about this kind of thing is, people are going to try to make every object a concurrent object. That is not the point. String is an example. And by the way, for completeness, one thing that is useful is that you can do the same thing with OStream. Notice that this is the same code as before, that I showed before, but with a concurrent OStream ref instead of a monitor of OStream ref. This is now a completely asynchronous cout, which I wrote again in just a few lines of code. I just used the same concurrent thing, the helper that we just wrote, and it works very nicely. Just use async cout. Now, and of course, here it is with the lambda, with the polymorphic lambda. But the thing is, you don't want everything to be asynchronous. So for cout, yes, you may well. In fact, I would recommend you have an async cout that you all use, and do it with a file stream or something like a log stream, that kind of thing, because you want things to be buffered and asynchronous. However, don't make every little object. Find out what are the logical entities that are used together that should operate asynchronously. What if you want to get work off a background thread, for example, off a foreground thread onto a background thread? So I believe I have an example next. Let me just go forward a little bit, and then I'll come back. Yes, so here's the example that I have a few slides from now, and then we'll come back and cover the rest. But say, for example, that you have a GUI thread or some other high availability thread you do not want to block. You do not want to do work on this thread. That thread has to be in the business of just pushing work onto the background thread and immediately continuing so as to keep on pumping messages, keep on redrawing the screen, keep on responding to clicks, that kind of thing. So what it does is it takes all of its data, which could be quite a bit. This could be a whole big pointer chasing graph of objects in memory. I want to concurrent that. And then in every member function, I simply take the contents of the member function, take the parameters, and say, execute the body of this function asynchronously. So if you look at what's happening here, and I'll talk about the return type in a second, that's what I just skipped over. Every function, like save, I want to save a string on the GUI thread. So I want to call this backgrounder save to this string file. It immediately makes a lambda that packages up a reference to the data, and, or sorry, the packages up a functor which when called, there it is, will be given the data. And so there's an object of that type in here. Here's the data type. And then all of this work inside the save function, inside its lambda, will be executed on this background thread. And the same for print. I can create another lambda that takes this data, does whatever it wants to do with its private data, which I've just made a nested type. And so I just follow this pattern, and with just this extra syntax on the front of every member function, I've made all my member functions asynchronous. So now I've got this nice backgrounder object where I can just push work onto a background thread. But you're right. You do not want to abuse this to make every little string in your object, in your system asynchronous. You will fall over and die. So people should not abuse the pattern that way. But whatever can be made asynchronous, think about whatever is shared that you might have thought of protecting with a mutex, see if you can make it asynchronous instead. Then you won't block on it. Remember, sharing causes contention. Sharing is evil. We want to reduce the amount of shared state regardless of how we protect it, with a mutex or a queue. But when you do have something shared, and you do want to protect here this logical piece of, which is usually quite a bit of data together, consider a mutex and consider a concurrent kind of object, a queue. Prefer the concurrent non-blocking one when it makes sense. Now, I skipped over the part, if I go back a couple of pages, to the one thing we didn't have is a correct function call operator that returned the return type. So I won't dwell on the details here, but here's how you write it, and this code works. Since I'm going to invoke f of t, remember with the monitor of t, I returned decal type of f of t. Like whatever invoking f of t returns, return that. Well, here in the concurrent world, I want to return a future of decal type f of t. So a ticket redeemable for this thing, whenever I finish executing it, the result it produces. So the way you do that, the incantation in C++11 is to make a promise. Notice there's the stood promise, and I make the stood promise of the correct type, decal type f of t. I then get a future from it, and I put the promise here. This is the function I push into the queue to be executed on the background thread. I push the promise, I capture it, put it into the background thread, and I try to execute f of t. If that succeeds, I set its value. Otherwise, I set an exception. And that I push on, but I don't wait for it to execute. This is what will eventually execute on the background thread, and I immediately return the future. So I create the promise in the future, send the promise in to be filled when I execute the thing, immediately return the future, and now I get out of the way, the caller can keep running, and I've queued up the work which will eventually complete. There is a problem with this code. What is it? What happens if you dereference the future after the promise has gone away? I believe that's not an issue here because the promise is going to fill itself. It's going to execute sometime, and you either are going to look at the future or you're not. But future set value has two overloads. It has this one, and it has an empty one that takes nothing for void. This won't compile if t is void. To make that work, you call a helper, and I'll let you read the code at home. You call a helper, which basically you overload for promise of something and promise of void. And inside promise of something, you call the code we just said. And inside promise of void, you just call f of t and then call set value, which does nothing. It would be nice if this was a little more template friendly, but this isn't so bad. And if you're doing this a lot, you might as well just keep these around to call, because this is how you set the promise and take care of the void case as well. So the question, somebody asked, how does async work? And Scott's pointing out this is the essence of async. That's exactly correct. In fact, that's a pretty good implementation of async. Well, actually, Anthony would know a better implementation, I'm sure, but this does pretty much the stuff async needs to do. Yeah. So if f of t, the reason we do this, of course, is if f of t succeeds, we set the value. But if it throws, we correctly store and propagate the exception. So if you hearken back to day 1, where Andre talked about is expected of t, it does something very similar for futures, and so you'll be familiar with this style. So here's how you use return values, just a straw man example to show you can use the return value. I have a concurrent string. I pass it some work to be done, and let's say it returns whatever. It returns some computed string type. I just get a future to that, and then I can do other work and then eventually call .get if that's what I want to do, or .then in the future, and then that will wait for the work to complete if necessary, and then use the result. And again, post C++11, we'll have a nicer time with polymorphic lambdas, which will make this even lighter syntax. So we talked about this slide already. In summary, we have the blocking part. What we're missing is the non-blocking part. It's on the way. And we talked about workarounds for how you can build future.then for yourself today, externally to future. So you could say then, future instead of future.then. And you probably have a concurrent queue in your concurrency library of choice, on your operating system of choice. You can build concurrent T today. And my hope is that in a few years you can write concurrent of T in portable isoconforming code that is also efficient, with an efficient implementation of future.then and a standard implementation of a concurrent queue. Now, one last coda, and we're right at time, but this harkens back to something that Scott said on day 1. Future and shared future destructors do not join. This is good because remember, joining or blocking is bad, except when they're spawned from an async. Here are reasons why this is a bad idea and we should fix it in the standard. Consider these two pieces of code. I say async f, async g, or auto f1 equals async f, auto f2 equals async g. Would you expect those two to do the same thing? How many would expect that to do the same thing? Why doesn't it do the same thing? Because the future destructor joins, which means the left-hand side is not asynchronous at all. You have to capture the future and make it live a little longer for these two pieces of work to overlap. So as long as future may join when coming from an async, those two can't be the same. And there's, from the usability point of view, which I like to look at, as well as efficiency, those really ought to be the same thing. It's a surprise that they're not. Here's another one. Let's say you write this code in a block. Async, launch async, darn it, F. Async, really, really launch async, G. Would it surprise you to learn that there's no concurrency at all in this code? To me, that's a bug. And this is only true of async. And here's a really bad one. Last example. If I have a function, and I say future of int f equals start some work, and then I do more code that doesn't get or wait. Call some function that returns a future, does something else, and then returns. Does that code block? Yes or no? So you don't know. If start some work returns a future that is a move of a move of a move of a move of something that eventually was launched, withstood async, this function will block before exiting its scope. Otherwise, it won't. That is not composable. We have to know whether our code blocks. The fact that this is true means I cannot use this kind of code, which means I cannot use futures reliably on a GUI thread, on any highly responsive thread, because I don't know, at least on this style, because I don't know if this is going to block. I have to be paranoid about maybe there was an async somewhere. It doesn't help that we're teaching the world correctly. They should be using async as their default launcher. That is what you should be using. So that makes this bad. Further, if it could be called, if this function could be called under a lock, that the task itself, which whatever it is, might also need, there's a potential for a deadlock here. So these are all very bad things, and the reason why the committee is looking at changing this to make it clear, no, really, we were just not right that time. Even in async, future destructors never block. In fact, the future destructor paragraph in the standard says doesn't block. It's only over in the async part that it says, by the way, if you call async, the future gives you blocks in its destructor. So it's the only type in the whole world the only function in the whole world for which this is true. So the right answer is don't stop, keep going, prefer non-blocking code. Now get caffeinated and be ready as we get back together in about 15 minutes for a final panel.